I was reading about the early Industrial Revolution, and it's kind of wild to think how much of it ran on, well, basically controlled explosions, steam boilers.
Oh, absolutely.
Yeah.
Especially the high-pressure ones. They were incredibly dangerous. Lots of accidents, sadly.
Right. But what if someone way back then, like over 200 years ago, came up with a safer way, quieter too, and could run on pretty much any heat you threw at it?
Well, someone did. Robert Stirling. 1816, he patented his engine, specifically designed to get away from those steam boiler explosions.
That's the Stirling engine. And it's kind of ironic, isn't it? Limited by the materials they had back then, but now it's crucial for some really advanced stuff.
Exactly. Deep sea missions,
Yeah.
space travel.
Yeah. So that's our deep dive today. We're going to unpack the Stirling engine, the core ideas, the history, and the clever engineering behind it all. It's a neat piece of tech.
Yeah, it really is. And fundamentally, you can define it pretty simply for everyone listening. It's a closed-cycle regenerative heat engine,
Closed cycle meaning.
meaning the working gas could be air, could be helium, hydrogen it's sealed inside permanently. It just cycles back and forth.
Okay. And it turns heat into work.
Right. External heat, the gas expands when hot, contracts when cold, pushing a piston. And the clever part, no valves, no timing chain, none of that internal combustion complexity.
It sounds almost too simple. How does it actually get decent work out of just heating and cooling gas without, blowing up?
Well, the core thermodynamic cycle is key. You compress the gas when it's cold, takes less energy, and then you let it expand when it's hot. Hot gas pushes harder,
Right.
higher pressure.
So you get a net positive work output from that difference. But the real magic, the thing that truly defines a Stirling engine, is the regenerator.
Okay, the regenerator, that sounds important, like the secret sauce.
It absolutely is. Think of it like a thermal sponge or maybe a heat flywheel. It's basically an internal heat exchanger, often just wire mesh.
As the hot gas moves towards the cold side, it passes through this mesh and dumps a lot of its heat into it. Then when the cold gas flows back towards the hot end,
It picks that stored heat back up.
precisely, it preheats the gas before it even reaches the main heater. That recycling of internal heat dramatically boosts the thermal efficiency. Without it, it's just a fairly inefficient hot air engine, really.
And that ties into the external heat thing, too, because the heat comes from outside.
That's the defining advantage. You supply heat through a solid wall, basically. So
Right.
it doesn't care what's making the heat. Solar concentrators, geothermal energy, burning landfill gas, waste heat from a factory. Anything hot enough works.
But that's also the catch, right? Especially back in Stirling's time.
Yeah, the materials science challenge. You need that heat exchanger, the hot end, to handle really high temperatures, high internal pressure, cycle after cycle, without failing, leaking, or just falling apart. That was tough in the 19th century.
I can imagine. Keeping high-pressure hydrogen or helium sealed in when it's red hot, tricky. Does the engine's physical layout, the configuration, help with that? I've heard of alpha, beta, gamma types.
It does, yeah. Those are just different ways to arrange the pistons and move the gas around.
Hmm.
The alpha uses two separate power pistons, one hot, one cold. Good power density, but
Seals on the hot side are a problem.
big problem. Very hard to make them last. So the beta and gamma types use a different approach. They have a displacer piston.
A displacer.
Yeah, it's sort of loose-fitting. Its main job is just to shuttle the gas between the hot and cold ends. The power piston stays on the colder side, where the seals have a much easier life. Beta has the displacer and power piston in the same cylinder. Gamma puts them in connected cylinders.
Okay, so those design choices involve some pretty complex trade-offs. Materials, heat transfer, longevity. Getting that right must require some serious know-how.
Oh, definitely. Optimizing things like heat exchangers or even figuring out where new tools like, say, AI agents could best improve performance or design that often needs specialist help.
Which actually brings us to our sponsor, Embersilk. If you're tackling complex technical challenges, maybe it's AI training, automation, software development, or figuring out integrations.
Or even just exploring where AI could make the biggest difference for your business, or even personally. Embersilk has that deep technical expertise.
Check them out at embersilk.com for your AI needs.
So yeah, embersilk.com. Now, back to the engine. You mentioned working fluids.
Right. Hydrogen and helium give the best performance.
Highest power density, yeah. They transfer heat really well. But they're small molecules, hard to contain, especially when hot. Air or nitrogen are easier, safer, but less powerful. It's always a trade-off. And that need for robust, often expensive materials for the hot parts contributes to the engine's main drawbacks. Relatively low specific power, meaning They're kind of big for the power they produce and higher initial cost.
So given those drawbacks, where do they actually shine today? What applications justify the size and expense?
It's all about the unique advantages. Niche applications, usually high-value ones. Submarines are a classic example.
Because they're quiet.
Exceptionally quiet. No combustion noise, no valve clatter. When submerged, running maybe on diesel and stored liquid oxygen, that silence is a massive tactical advantage.
Makes sense. And what about at the really extreme end? Reliability, exotic heat sources.
Yeah, you see them in concentrated solar power, CSP, big mirrored dishes focusing sunlight onto the engine's hot end, very efficient. And then there's space.
Yes.
Yep, for deep space missions where you need power for decades with zero maintenance. Think radioisotope heat sources, basically a chunk of plutonium keeping things hot. NASA's crusty reactor concept uses Stirling engines. They're efficient, reliable, and don't need air or fuel deliveries light years from Earth.
So it's like the engine was born from a 19th century problem, dangerous steam, but the 19th century couldn't quite build it right. Now, with 21st century materials and know-how.
Exactly. Its fundamental principles, safety, quietness, efficiency, fuel flexibility, are arguably more relevant now than ever, especially as we look towards, renewables and decentralized power.
That quiet efficiency finally having its moment. A great thought to leave things on.
It really is quite something.
Well, if you enjoyed this deep dive, please do subscribe to the show. And hey, if you have a moment, maybe leave us a 5-star review. It genuinely helps get the word out. Thanks for tuning in.